can do that, that's a cleaner way to test the difference. So we've got the regression equation, right? The logit, the log odds, is equal to 4.6123 minus 0.4411 times parent schooling. We can convert those to probabilities back with that formula we looked at earlier. I mean, instead of just talking about, well, what's the odds ratio, we can actually say, well, what if a kid is in, a specific grade? Let's say someone is in 7th grade. What's the probability based on this model? What would I predict is the probability that they'll drop out, that there'll be a 1? Remember, that's what we're predicting, the probability there'll be a 1 or drop out. So you just take this funny looking formula, 1 divided by 1 plus e to the negative regression equation. You just plug in the regression equation, or you can solve the regression equation and plug in the value. Make sure you do negative, whatever that value is. So we do 1 over 1 plus e to the negative 4.6123 minus 0.44111 times 7 gives us 1 over 1 plus e to the negative 4.6 minus 3.08, or 1 over 1 plus e to the negative 1.52, or 1 over 1 plus 0.2177, or 0.8212. That's the probability, that's our predicted probability of dropping out if the parents had 7 years of schooling. We can do the exact same thing with a different value. What about if they had 12 years of schooling? And we just take the exact same equation, but now we plug in a 12. And you get blah, 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 down to 1 over 1 plus e to the negative 4.6 minus 5.29, or 1 over 1 plus e to the negative 0.68. Keep track of those double negatives, which is 1 over 1 plus 1 over 1 plus 1.979, 1 over 1 plus 1.9757, or 0.3361 is the probability with 12 years of schooling. It is a tough school, tough community. Okay? So you can do that, and you can see, if we start to run out of time, how you could plug in all sorts of different values and create a graph, a figure of those probabilities for different values to get a sense of kind of not just the odds ratio that tells you the effect of cumulated, when you're kind of increasing risk, but also kind of the overall probabilities across the whole range. Another way of evaluating a logistic regression is based on how well it accurately predicts your outcome correctly. In that sense, it's a little cleaner than with multiple regression, right? We have our regression equation, but we know that the variables rarely are going to fall exactly on that regression line. And we look at things like the R-squared, and the residuals, to kind of see how closely they're clustered around that regression line. Well, in logistic regression, our outcome is 0 or 1. We can actually look at that. We can look to see kind of how would we predict, are they a 0 or 1? And again, most output will give you some option like this. We are looking at what's called a classification table. You have the observed outcomes. Did the child graduate or drop out? And then their predicted outcomes. Based on my regression model, my logistic regression model, did I predict that they'd graduate or did I predict that they'd drop out? Now, this is based on, there's some cutoff. Notice it says the cut value is 0.5. That's just kind of, it's saying, well, if I plug in your value and the probability is greater than 0.5, I'm going to say you're a 1. If If it's less than 0.5, I'm going to say you're a 0. So that's how it's making that cutoff decision, which we'll talk about in just a sec. And you can see in this case, our model predicted 26 kids were going to graduate. Of those 26 kids, 28 did graduate, and the model said 8 were going to, but in fact they dropped out. And our model said 24 kids were going to drop out, and of those 24, 17 in fact did drop out, and 7 our model predicted would drop out, but in fact the kid did not. So overall the model is right for 28 kids here and 17 kids here, which is 45 kids out of a total of 60 kids, or overall the model is right 75% of the time. Is that good? Is that bad? Well, it kind of depends. I'm going to jump ahead and I'm going to, well, no. We'll come right back to that. Kind of as we just said, the model's right 75% of the time. Notice it's wrong for these 15 kids. There's 7 kids that the model predicted would drop out and they actually graduated. You may see these referred to as false positives. They're being flagged as a concern, but they're not. It's like, screening tests. The test will say, oh, there's a problem, but then everything's fine. Then there's these 8 kids that the model predicted would graduate, everything's fine, don't worry about this kid, but in fact they dropped out. So they're false negatives. So depending on your question, depending on your research, these may or may not be big deals. And some may be a bigger deal than the other. You may not mind false positives, but you don't want to miss any false negatives. That's actually something you see in screening. The newborn screening that Shafan and I are involved with for hearing screening. 6 out of 7 babies are false that fail their screen. 6 out of 7 of them are false positives. They actually go on, they get the full testing, and everything's fine. But you don't want to miss the philosophy is you don't want to miss the kids who actually do have hearing loss. So you're willing to say, okay, we'll let this number be a little big because we don't want to be telling kids everything's fine, only to find out 3 years later, little Timmy can't hear for the last 3 years. So, you need to kind of think how to evaluate all these is a question. Don't look at a number and say, 75%, everything's good. Look at kind of what are the consequences of false positives, false negatives. Even beyond that, classification results can be misleading. For example, I can tell you right now, how much would you pay for a diagnostic test, a screening test that can tell you with 98% certainty whether a child has autism at birth? Isn't that worth money? I mean, if I can do this, wouldn't you think the state would be paying me $20 a kid? With 98% certainty, I can tell you whether a child has autism at birth. And I'm right 98% of the time. You know how I do it? I say, every baby, I say, you don't have autism, you don't have autism, you don't have autism, you don't have autism, you don't have... I say, no kids have autism, I'm right 98% of the time. There's actually people that have made money doing stuff like this, not on autism. But you predict things that are very rare, and you have a lot of false negatives, and your results can look really good. I've got to find it. I had a paper and I can't find it. Years ago, reviewed this whole sort of literature, looked at all sorts of studies in terms of how do people evaluate false positives, false negatives, accuracy rates. Because there's like, they came up with like 8 different ways you can slice and dice the numbers. And they found overwhelmingly, far beyond statistical chance, people always picked the way of the error rate, the error number that made them look the best. Some people are saying this, some people are focusing it this way, and it always somehow happens that the number they chose is the number that looked the best. So just looking at the classification results can be tricky. Look at that again. If you've got a lot in one category or the other, it may be very easy to get very good prediction. In which case, you may want to look at the false positives, false negatives, or look at how much is actually gained from going from a model knowing nothing to a model that you're paying $20 a kid for. And you'll see there's nothing gained. Okay? As we said a few minutes ago, you can actually use your values. B1, make that a 1. And just plug in, you can do this in Excel. Just plug, type in the logistic regression equation, put in your, put in values of X, and you can generate a nice little plot. Here's our predicted probabilities across the range of parent education. That's kind of cool. This will definitely impress your committee. And you can see, notice as we saw when we did that, when I made it extreme all the way to negative 35 years of education and positive 40 years of and it was kind of very nonlinear, right? You can see it's a little nonlinear. It's starting to level off here, and it's starting to level off there. Within the realistic range, it's more linear than, but again, the beauty is we know it can level off. So that's the power of this approach. Again, all you do to do this, you just take your regression equation. Well, you take the model, the formula for calculating probabilities, plug in the regression equation, make sure you take the negative, e to the negative of that, plug in a bunch of values for parent schooling, and graph it. Now, what's kind of interesting, something to keep in mind with this, remember, this is just the model. Just like with multiple regression, we talked about, look at your equation, look at the real data. Because sometimes it's as much as I love regression models, they're just models. They're not necessarily reality. So let's kind of take a look at, here is our regression model, and here's the predicted scores. The line is those predicted scores from our model. Here's the actual probabilities that we saw in the real data. And you kind of see, well, it's kind of, it's doing pretty good here. But something happens at 12th grade. Notice there's a big drop at 12th grade, and then it kind of levels off, once you graduate high school. So, and it's not capturing that here. It's not quite, it's missing something. So I'd want to keep tweaking with this if it was me, if this was real data. So again, kind of look at what that reality is. There's a more fundamental problem. I mean, this kind of starts to touch on, again, as much as these are neat techniques, you can have a more extreme example. And this actually, unfortunately, this one isn't the real data, but because, well, it was done long ago and I can't find the original write-up we did, and the paper got rejected. Now it's like it's disappeared into my messiness of what is my life. But this was basically what we saw. we were doing it for a quantitative methods paper, and the reviewer didn't like, they saw no need for what is so obvious to me. There's a need. Someday I got to redo this and try it again. I think we might have just been too early. So this is a model. Let's look at mother education, predicting kids who are in special education. This was Florida data. Again, this isn't real data, but this is what we saw that kind of caught our attention. This is reality, this red line. And what you saw, so what we did, let me take a step back. So what we did is we were looking at levels of maternal education, predicting whether or not a child ended up in special education 10 years later. Didn't matter kind of what the category was, just is the child receiving special education services. Kind of the idea is the environment, home environment, whatever factors that may be influencing things. And we ran a logistic regression, sure enough found a significant effect for mother's education. And it didn't quite, if you plot the probabilities, it didn't quite look this clean. But it kind of, it looked close to what this blue line is. But when you look at reality, it was very different. You saw an asymptote at the low end, but the asymptote was nowhere near 1. It leveled off at about like 40%. In that sense, once you got below a certain level of parent education, it really didn't matter. About 40% of the kids were in special education. Whether you had, and this was because you're dealing with a lot of immigrant from poor third world countries that didn't have a lot of education. So you had a fair number down here. If you're kind of wondering, was there just no one down there? At a low level at a low value, it leveled off at about 0.4, and that was, it didn't keep going. It was never getting close to 1. And this makes sense. I think this one makes even more sense. When you get in, no matter how much education the parent has, there's some percentage of kids who are going to be in special ed. There just is. No matter what your home environment is, how educated mom and dad are, there's going to be, kids with autism, kids with hearing loss, kids with, so it's going to asymptote at a different level. Logistic regression can't handle that. If you really have hard asymptotes where it's leveling off, you need a generalized logistic regression approach, which was what our whole paper was talking about. And they said, oh, that's silly. You can always make it asymptote. So our response was, yes, our response was like, what? I mean, yeah, you can add variables to artificially, it doesn't make any, that was very frustrating. It's so obvious. That's a problem. But anyway, so again, always look at the real data. And if you are doing a study and you get something like this, come see me, because we got a paper. we can write that up. If your data, you can be first author. I'm happy being at the end, and we can do a really cool generalized model. So anyway, again, just kind of emphasizing, look at the real data. Kind of look, how does the reality reflect the model that I'm coming from? And this sort of issue is something that the nice thing with logistic regression is it asymptotes. You can deal with those issues of the kid's behavior can't go on and on and on, and it deals with that leveling off that we saw multiple regression can't. The problem or limitation with logistic regression is it has to do it at those two values. There's no flexibility where it can level off. There's more techniques that you need to make an even more complicated model to go there, which we won't deal with. So that is our introduction to logistic regression. I mean, you can see